For my project, I modeled the heat block on a 3D printer. As you can see on the picture on the right, the heat block is a rectangular shape near the bottom. This has a heater cartridge in it. The heat block's purpose is to heat up the nozzle, which melts and lays down the filament. Above the heat block is the heat break, which is designed to prevent heat creep. The heat break is placed in an array of fins to promote greater heat transfer. I modeled the heat block using an energy balance, E dot stored equals E dot gen minus E dot out. E dot gen is simply voltage times current. E dot stored is density times volume times specific heat times the temperature difference over time. E dot out is a combination of convection and radiation. On this model, there is no fan cooling the fins or heat break, so there is only free convection. Free convection on opposing sides are the same and will use the same H value. Combined with free convection on the top and bottom surfaces means there are 4 H values that will need to be found during each iteration. HR will also need to be found. The emistivity is assumed to be 0.5. This model uses Euler's method coded in Python to solve the temperature difference in the heat block. The model assumes that the heat block is made of T6 6061 aluminum with a constant specific heat. The air properties are set up to be interpolated during each time step as the model heats up. T infinity and T surroundings are assumed to be the same. When the model was solved the first time, a constant E dot gen of 20 watts was used over a time of 150 seconds. Upon inspection of the data output, the results in the graph seemed reasonable. To verify the Python code was working, the first several time steps were solved in Mathematica. The two gave the same answers, which gave more confidence in the code being used to solve the model. By using a watt meter that was placed in line with the power supply on the 3D printer that was being modeled, the energy used over time was recorded every second as the printer heated up to a temperature of 200 degrees C with about 10 degrees C of overshoot. This power measured was taken as the heat block was in the configuration shown on the right. As is seen, the model reached over 300 degrees C and settled over 250 degrees C, well over the measured value. It was thought that there was a significant amount of energy going into the heat break and nozzle. They were removed for the next test. The power usage was measured again while the heat block was in the position shown. The power usage data was then placed into the model. The model still reached over 300 degrees C and settled around 250 degrees C, still way over what was measured. Still on the heater block was a small metal plate that holds the thermistor securely into place. Even though it wasn't expected that this place would have had that much of an effect, it was also removed for the next test. The power usage was again recorded and placed into the model. As can be seen on the graph, there was almost no change in the output from the previous test. Upon further inspection of the heater cartridge in the heat block, it was seen that the cartridge is held securely into place by a screw that pushes perpendicular against the cartridge. This leaves an air gap around some of the heater cartridge. This can somewhat be seen on the picture on the left. It was estimated that only 5/8 of the heater cartridge was in direct contact with the heat block. Recognizing that significantly more heat will be transferred through direct contact than when there is an air gap between, we will multiply each measured power input by 5/8 and see if that gets closer to the experimental data. On a side note, after some research, it seems that the heat block shown on the right is more common, which has a screw that tightens the heat block around the cartridge. After taking the power usage data from the last test and multiplying each time step by 5/8 and placing it into the model, the output can be seen along with the experimental output. The final temperature of the model is around 168 degrees C, well below what was seen in earlier tests. There is about a 15% error from the final temperature of the experimental final temperature of 199 degrees C. A few interesting things to notice, however. In the experimental data, it can be seen that it takes a few seconds before the heating up becomes linear, like it takes a moment to get going, whereas in the model it immediately starts going up and linear. Also in the model, once E dot gen is shown to be shut off, it immediately starts going down, whereas in the experimental data it levels off more and takes a second to start cooling down. This makes sense as the heater cartridge is still hot and could still be transferring some heat to the heat block. To improve on this model, the first thing that should be done is upgrading the heat block to a more standard heat block that will allow for more heat transfer. By doing this, we can have more confidence that all of the energy being measured by the watt meter is going into the heat block. One of the assumptions made at the beginning of this experiment was that T infinity and T surroundings were the same. It would be beneficial to measure what exactly T surrounding is so that the radiation heat transfer is more accurate. Also, in measuring the power input to the printer, an average power usage by the printer before the heater cartridge was turned on was found and subtracted from the total power usage by the printer while the printer was heating up. The power usage before the printer turned on fluctuated roughly between 1.2 and 2.0 watts and was averaged to 1.6 watts. Measuring the power usage to the heater cartridge directly would supply the model with the most accurate E.gen values.